All right. We want to see how many missing values we have in our dataset. We do so by calling the isNaN function and method chaining .sum at the end of the line. Wow! The output reads 88,005. That's a lot of missing values we need to take care of. With that in mind, let's create two temporary variables called temporary fill and temporary mean. The first one will store the rounded result of NaN max plus 1. And the second variable will contain the outputs of NaN mean ran over the 0th axis. The former will be greater than any actual value from the dataset, so it will serve as a filler for all the missing entries of the dataset, while the latter will hold the means for every column. Running the cell raises a runtime warning. Unlike errors, warnings don't prevent the code from compiling. Instead, such messages alert the user that they might be overlooking something. Besides, if we look at the warning, the number following the colon, 2 in this case, informs us which line of the cell we should examine. In other words, the message states we are plugging in empty slices to NaN mean. Thus, provided that by construction the function ignores NaN values, and we're running it along every column, there must exist entire columns full of only NaNs within the dataset. So, based on the warning error, it looks like we have at least one empty column. However, that's not entirely true. The default data type for generate from text is float, so a column of only strings is automatically filled with NaNs and considered empty. This means that we might be observing missing values now, but the dataset may in fact contain important text data. To determine exactly how many columns consist entirely of text values, in a new cell, we can display temporary mean. We see 8 columns that have NaN as their mean, which tells us they only store strings. To elaborate, if even a single row of a column isn't an NaN, then the NaN mean would return its value as the mean. Therefore, any column with a mean of NaN contains no numbers. However, NumPy doesn't usually like it when we store multiple types of data, like numbers and text, in the same array, since it limits what we can do with the dataset. Hence, we should split the data into two smaller arrays, one containing the numeric values and another one, the strings. Before we do so, we should extract the minimum and maximum values for each numeric column, since we'll be substituting those into the dataset later on. As we explained earlier, the head of data analytics has given us casting directions on how to fill out the missing values for each column. For convenience, we'll create a variable called temporary stats, which is short for temporary statistics, and set it equal to NP array. Within the parentheses, we'll add a list which contains the following: the output of the NaN min function for raw data NP along the 0th axis, the temporary mean from a few minutes ago, and the output of NaN max. We get 2 more warnings that indicate we're plugging in empty slices. As we explained earlier, those are simply full of text, so we don't need to worry about them right now. We can instead go to a new cell and display the temporary stats variable. The output consists of a 2D array that holds 3 one-dimensional arrays stacked on top of each other. If we compare it to the output of the previous cell, it is obvious that temporary mean is the second one of these arrays. Of course, mean is the middle row by construction, since we wanted to have the mins first and the maxes last. Therefore, the order is maintained. Everything seems good, and we can move ahead. In the next lecture, we'll split our data into numerical and string data. See you there.